Did you know that the standard cell potential can be related to Gibbs free energy? I mean, I kind of hinted at it at the very first video, so you probably were expecting this. But we have an equation that will directly relate the standard delta G to the standard cell potential. So standard delta G is equal to negative NF E cell. The N is the number of moles of electrons transferred in the balanced reaction. So in the overall balanced reaction, how many electrons were transferred? If you want to look back at the iron example that we did for writing the shorthand notation, we had an equation that had like 5 iron turning into 5 iron 2 plus. The N for that reaction is 10. It's the 10 moles of electrons that were needed in the balanced reaction. F is Faraday's constant. It's 96485 coulombs per mole of electron. So you can see here, because of the negative sign, if E cell is positive, then delta G is negative, which is how you get spontaneous or thermodynamically favored. A negative E cell would be a positive delta G, which would be not favored. For units, let's just kind of set up the units here. So the N was moles of electrons, so moles. Then Faraday's constant is coulombs per mole of electron. And then E cell was in volts, but that's a joule per coulomb. So you will get joules as your units out of this equation. We also have a relationship between standard cell potential and the equilibrium constant. So the standard cell potential equals RT over NF times the natural log of the equilibrium constant. And N and F here are the same thing that they were in the earlier equation. Thankfully, because we do this under standard conditions so often, there are versions of this equation that have put all of the constants in for you. So strongly recommend using one of those versions. The one I have here, please note that the natural log is now a regular log. So part of the conversion was getting rid of the natural log. I don't know, you might like regular logs better. So if you are at 25 degrees, the standard cell potential is 0.05917 volts divided by N times the log of the equilibrium constant. So where this puts us is in our standard delta G, standard cell potential, equilibrium constant triangle. We have a way to convert between all of these. So between standard cell potential and standard delta G, this is the new equation that we have of negative NF E cell. The E cell and the KEQ, we have this new equation of standard cell potential being 0.05917 over N times the log of KEQ. And the equation that we already know, which is that the standard delta G is equal to negative RT ln of KEQ. So if you have any one of these, you can find any of the others. So this is all under standard conditions. What about non-standard conditions? So E cell represents a potential. As the reaction runs, that potential is used up. So as soon as we get into non-standard conditions, we need an equation that lets us adjust for how far from standard we are. And that is the Nernst equation. So the cell potential is equal to the standard cell potential minus RT over NF ln of Q. And this is the same Q that we had before. It is the reaction quotient. It tells you where you are in a reaction. Now, at 25 degrees Celsius, we can substitute in for these constants. And I have both versions here, so you can choose if you want to use log or natural log. But the cell potential is equal to the standard cell potential minus some constant that you have to factor in the number of moles of electrons still, and then some version of a log and the reaction quotient. The most common non-standard example you will see is a concentration cell. So the reason a concentration cell will run is because of non-standard conditions. So you'll see why when we calculate the standard cell potential. But let's set up this concentration cell. So on the anode side, I have solid copper and copper 2 plus. On the cathode side, I have solid copper and copper 2 plus, but their concentrations are very different. So I have 0.010 molar at the anode, 2 molar at the cathode. So unequal concentrations, you could predict where this was going without anything that we have done in electrochemistry. So hopefully you would predict that this will run in the direction that equalizes the concentrations, and that is exactly true. So let's say that this is our cell, and I want to calculate delta G or the standard cell potential or something like that for it. No matter what, I have to start with a standard cell potential, and my reactions are the same. So my oxidation side is copper turning into copper 2 plus, and my reduction side is copper 2 plus turning into copper. So when I look up my standard potential for the electrode, it's 0.34 for both of them. So 0.34 minus 0.34 is 0. If these were standard conditions, which would be noted by it saying 1 molar or not having a concentration listed, this cell would not run. So it will only run because my concentrations are different. And right, if I want to know the E cell for that, I need to figure out a couple of things. So I need to know the number of moles of electrons transferred. Well, I have my oxidation and reduction reactions set up separately here. This would be balanced. I could add these together. So in the balanced reaction, I'm transferring 2 electrons. So my N is 2. Now, also, in my overall reaction, the reason I have this in different colors, when you add it together, right, the orange is oxidation and the blue is reduction. So copper solid plus copper 2 plus. The copper solid is from the oxidation reaction. The copper 2 plus is from the reduction reaction. So the reactant copper 2 plus is the 2 molar concentration. This is turning into copper 2 plus from the oxidation half reaction, which has a concentration of 0.010, and solid copper in the reduction side. So also, this looks like it's set up right. I'm going to use up the high concentration copper, and I'm going to make copper on the side that's starting out with a lower concentration. This gives me enough information to set up my reaction quotient. My reaction quotient is the concentration of copper 2 plus over the concentration of copper 2 plus. But we have set this up so that you know which is the product and which is the reactant. So it's the orange copper 2 plus over the blue copper 2 plus, which is the 0.010 divided by 2. That is my Q value. So my cell potential is 0, which was my standard cell potential, minus 0.05917 divided by 2 times the log of 0.010 over 2, and I get 0.068 volts out of this. So a positive value for the cell potential means that this will run spontaneously. It's thermodynamically favored, but it is only doing so because of those concentration differences.